Hello, everyone. In this video, I'm going to talk about some terminology that has to do with the background. And of course, this terminology is important. Um, if you have an equation that involves derivative of one variable, so let's say you have an equation that involves one variable with respect to another. Then, of course, the variable, the first one here is going to be called the dependent variable, and this other variable is going to be called independent. Just like you've done before, let's say making somebody works per hour and makes, let's say, $20 an hour, then the income here is going to change based on how many hours are worked. So the income is going to be the dependent variable, and the independent variable is going to be the hours, which is the time. If we have an ODE, let's say if we have, or let's first give an example. If you have a second derivative of position with respect to time here, and some constant or coefficient, and the first derivative with respect to time here, plus some coefficient kx equals 0. So here, x is going to be the dependent variable, and t is going to be the independent variable. So it's good to understand the format and when we look at it again. And rates of change were done before, but this is more of reinforcement. And AK here are coefficients. As you see, this equation involves only ordinary derivatives with single independent variable. So this independent variable time is kind of single here. We don't have t and x, or something else. We only have t. So in this case, that's called ODE, or ordinary differential equation. So this is an example of ODE. And let's put a kind of definition. In ODE, it involves only ordinary here derivatives with single independent variable. All right. So that will give you an idea about what to expect for a PDE, or a partial differential equation, more than one independent variable, more than one independent variable. All right. So I'll give examples. I'll give examples soon. So here, another important part to talk about here is the order. We need to understand the order, because when you understand the order, you understand some other ideas that follow, like Lewis-Lair conditions and stuff. So this is the highest derivative here is second. So here the order is 2. Okay, so the order is the highest order derivative. Not the highest exponent, but highest order derivative. Another important part to understand here, and it's essential in terminology, is linear. What is a linear DE? Of course, in many applications, linear is much preferred than nonlinear. And as you go a little more, you'll see that you take some nonlinear and you make them linear. And there is a lot of work on that side. So first, we need to recognize what's linear and not linear. Of course, going back to, let's say, algebra, we say this ax plus by equals c is a linear function, right? A line. If it's in 2D, if it's in 3D, you just add, let's say, the third dimension and like something like that. So based on this idea, the linear definition here will come. So the variables are going to appear in additive combinations of their first powers only. First powers only. You see, because if you have ax squared, then it's not linear anymore. All right, so a linear differential equation, then you have a dependent variable y and its derivative appear in additive combination of their first powers. So let's make it a little more precise. The dependent variable y let's see, can we, yeah, dependent variable. Let's write it. Don't have space to now fix it, so let's just write it again. So the dependent variable y and its derivatives appear in additive combinations of their first power, of their first powers. So what does that mean? Something like this. And x, let's say the nth derivative plus n minus 1, the nth minus 1 derivative, all the way to ax dy dx, the first derivative, and some last here where y shows up equals to f of x. All right. So let's say, example, what about this second derivative here plus y cubed equals 0? It said that this cube here will make it not linear. What about, let's look at another example. So this is examples. T cubed dx dt equal t cubed plus x. Let's try to mimic that first one and see what happens. So think about it. Pause the video and see what you think. All right, so as you see in this first one, y is a dependent variable. But here t is not a dependent variable, as you see, independent. So actually, although they look similar, this one is linear. Okay. The independent variable here is t, and the dependent variable is x. Let's do one more. You can pause the video and see what you think. All right, this one is non-linear, of course, because of this term here. All right, thank you.